All right, welcome to our ORI FPGA meetup. This is October 22nd, 2024. And what we do is we talk about what we have done over the past little bit of time, usually a week or two, what we have planned over the next week, if we have any roadblocks to the work that we want to do, and if we need any resources. So anybody with time constraints for the meeting is gets priority. Maybe Matthew, would you like to take the floor and talk about Opulent Voice?
Sure. And thank you. Yeah, I do need to drop off at 10:30. So, all right. Good morning. And as far as what I've been working on this last week, it's been not much. We were traveling last week, and then on our way home, my wife's aunt broke her ankle last Sunday, so we're in El Paso for a few days. So away from all my stuff, but I do plan to run some more simulations this week. I think you guys made some good progress with the hardware and identifying some issues. In my experience, the hardware and the simulations should always match. And every time they haven't matched, and I've been doing this for a lot of years now, it's either been a configuration issue, which I don't really think is the case here, or there's an underlying assumption about what's happening in the hardware that's not valid. And I kind of think my suspicion is that's the case here. So I had identified the TX enable and the RX enable as potentially interfering with the modem processes. We fixed those and we haven't seen really an improvement, although I think we are seeing some short durations now of 0-bit errors. And so I'd like to compare that to the simulation. I think my simulations have only been running, say, 40 or 50 milliseconds. I can extend them out. And so if that bit error rate duration is that or longer, then the simulations may not just be running long enough to identify a loop instability or something like that. So I'm hopeful we can kind of triangulate on this issue and have a good stable modem working on Pluto. And then the next thing, assuming that if we have any difficult, closing the loop, I do have all the components now to use integrated logic analyzer. So I have the two adapters I need. They're just at home, so I don't have them available this week. But at least, I have those, so I'd be able to start, we can start building with some integrated logic analyzers and looking at what's actually going on in the FPGA, and we can compare that to simulations and, hopefully identify something that's, whatever the root cause here is. So I think that's where things stand from my perspective.
Yeah, thank you so much. And very best wishes on quick recovery from the ankle. That's
Thank you.
A big deal. So yeah.
Thank you.
Yeah, and that's really good news about the ILA. So integrated logic analyzer, for those of you listening, is a really neat sort of block that you can add, or a block framework that you can add to your HDL design that gives you a lot of increased visibility into the design. And yes, you do need to have like you need to kind of up your game on your test bench in order to get more access. Good. JTAG is really, really kind of necessary to get the most out of it. And what we're trying to tackle is some kind of unexpected behavior from the loops. So our tracking loops for the costas loop and the IP, proportional integrator controller, or PID controller, is where you might have heard this before, and we have the P and the I part of it, and it's not really cooperating with us like we would like, and it's very true. It's either a configuration problem, or there's something that has been a misstep somewhere along the way in the code, and so that we're trying to work through this in a collaborative manner. And it's kind of the thing that we're providing through remote labs is deploying the design to actual hardware and seeing what happens, capturing the results, and kind of feeding them back to the authors. In this case, Matthew is the lead on that, and working through it. And yes, the TX enable and RX enable, that was a really good catch. Something that could have caused a sneaky little problem there. And it did not turn out to just magically solve the problem. And yes, a longer simulation time would be good. Um, yeah, so we're just going to keep working through it and keep going back through, making sure that all the registers are set up correctly, that we're giving it the right amount of time to run, um, and looking for things, and also working through the code on our own, like taking the source code and making sure that we understand what's going on. Um, so over the past day or so, I've been able to, like, I've made peace with the PI controller module or block of code. And this PI controller is encapsulated within the Costas loop um, logic. So there's a Costas loop module that uses the PI controller as kind of a sub component. Um, and I'm looking at it, and I think that the use of the alpha, which is the roll off of the filter, low pass filter. I'm not sure I understand uh, how that's working. Um, so I will.
Yeah, let me give a brief explanation there. So, because of the mixed components, when you mix the F1 and F2 with the LO, you're getting say the sine wave still comes through on the errors on the Q arm, which is the error arm. So you're integrating the error, which is sine theta, which is the phase offset from what it should be. Um, but then on top of that, sine theta is a sine wave is one of the mixed components. So my thinking was, that's that we if we put a low pass filter in the Q branch, it would clean up and make it easier for the loop to work. I'm not convinced that's really the case. So the alpha just sets the roll off factor. I should provide some documentation on the low pass filter, but it's basically an IIR filter, a very simple IIR filter. And so the more you increase the alpha, the steeper the roll off, but the trade off is it also increases the latency the steeper it is. And so at some point, if you get it, you can get a good steepness, but it impacts the loop because there's too much delay on the error signal. So in simulation, I found that it's the loop filter or the low pass filter is not really even needed. But we can still experiment with that by setting the alpha, but it's not part of the PI controller. It happens actually before the integrator in the Costas loop.
Right, yeah. This particular part of the logic is outside of the PI controller, which I'd still like to explore that a little bit more, because the dividers that are in there, like, I think maybe just check and make sure that they're not pulling us too far one way or the other.
Yeah,
It's on my list to, like, maybe that's the root cause. I don't really think so, because it's like so clear. It's, the tracking loop pulls off and goes kind of haywire so fast it can't. I don't think it's something like that, but it is on the list. My question about the alpha was, like, in the case where the alpha is set to 0, it looks like that there's no accumulator component that comes back at all. Like, the accumulator just no longer gets added back into the um the loop that's going on in the Costas loop.
right.
Um,
Well, I mean, again, the alpha is just for the low pass filter. So,
right. Yeah, so
and
when you
yeah,
set
so
it to 0, that's essentially supposed to be removing the
right,
filter, I think.
right.
Okay.
I think so too.
Okay.
It's a simple equation, so I just have to look it up, and
Yeah.
I
But
can send.
I was like, well, and so I just want to make sure that, like, when we set it to 0, that that's intended, that there is no accumulator value that's fed back in. Like, they
Right.
cancel each other out at that point.
Yes.
And if we were relying on some sort of value coming back in or being kept, like, there's now no memory at all with
Right.
this.
Yeah. Again, that when the papers that we've based this Costas loop on don't have the low pass filter. So it was just something I had added at one point to see if I could make the simulation work a little bit better. It was kind of a crutch, if you will, to
No,
get the simulation working.
because some of these papers do have low pass filters in them.
Yes, they
So
do.
I mean,
Yes.
it's and for good reason. It looks like so. I think that your instinct was good. So we may end up like completely removing it because I think you said a couple of weeks ago, it looked like that any alpha in there was acting in a negative manner. It
Right,
was
right.
not helping us like as expected. So anyway, I'll do the best I can to kind of focus on that and walk through the math and try to come up with some justifications for whether or not it should be in there as best I can. But so far, like working through the Costas loop, that with the exception of the alpha, uh, so far it looks like it makes sense. And what we're trying to do, at least in the lab, is set up a test that is a positive indicator of like, okay, we do this, it works, we do that, it doesn't. So far everything we've done, it doesn't work, but we're going to just keep looking for settings or for configurations or for anything that we can do through the registers that will cause anything that we can control it one way or the other. Because as soon as we get a handle on the loops, uh, I think that the rest of it, because we've seen the rest of it work in both simulation in Mathland. So once we get a handle on the loops, I think it's a bit of I can't say it's completely clear sailing, but it it really leaps forward from that point. So all of this is
Yeah,
effort very well spent.
yeah, those are the most critical part, I think, in the demodulation. I mean, they're integral to it. So, and
Yeah.
the TX looks pretty good from what we see in the spectrum. So,
Yeah, it
I,
does. It looks really pretty beautiful. So it's really nice to see the math come to life like that.
yeah,
And it's the tracking loops we'll sort it out. We're just gonna grind through it and keep at it.
yeah, it's
Um
not like we're doing anything new. That it's just figuring out what we did wrong.
yeah. Yeah.
Um, oh, and to the extent I was planning to run a long simulation on Chococat, but the Python test bench I'm using is giving me some fits, so I need to figure that out. It works fine on my MacBook, but it's a little unhappy on Chococat, so I just need to dig into that and then because I was planning to just let it run for a couple of days, we can let it, and we can probably get 500, 600 milliseconds at least if we do that.
Okay. No, that'll be very illuminative. So uh, yeah, if there's anything that we can do, Paul's probably the best person to ask for things on Chococat. And I saw that we did get some things properly installed, and they were working for this particular
Mm-hmm.
part of the project. But yeah, if there's anything that looks weird, let us know. And just
Yeah, we got
to
GHDL and GTK waves so that we can look at the waveforms, and then the GHDL would be the simulator.
Yeah, that's good stuff. And I won't steal from Paul's report, but he was able to solve the problem about local installs on Ubuntu laptops that we had during the digital update for microwave. So our little workshop that we had in Vancouver, we were not able to install the Pluto-MSK repo on just a local laptop. But he tracked down the reason why and is already submitted a pull request for that. So I'll let him report on that. But that was a good step forward there, and very appreciated. All right, anything else that you think we ought to pay attention to over the next week?
I think that's it from my perspective. Thank you.
Oh, no, thank you. This is super exciting. And yeah, just we'll keep our heads down and keep into the uh trying to figure out all the loops, Costas loops and tracking loops. That's most of the game right there. And just along with synchronization is like the big grippy part of digital signal processing and getting things to work over the air. So very exciting and and really looking forward to the next week of work. All right, so yeah, I'll hand it off to Paul if you want to talk about this and all the other stuff. And if you happen to have any of you've done some visualizations over the past week or so um, on like the tracking loop and accumulators and the behavior. So if you want to share that, that'd be fun to see.
Okay. I'll try to do that too. Um, I got a little list of things actually. Um, so I'm a little bit more organized than usual. One thing that happened since we met last week is that Matthew was able to recognize and solve a problem that would have stopped us dead in our tracks for probably days or more with the register, a bug in this in RDL, I think is the TLA for that.
Yeah, yeah, the registered descriptive language,
Yeah,
the
where
framework
you
that we're using for organizing our register accesses.
right. So it turns out that if you have some bits near the bottom and some bits near the top with a gap in between, that there's a problem with the compiler. And the solution is just to put reserved bits in between. But I don't know how long it would have taken us to figure that out. But we got that dispatched in short order by Matthew recognizing the problem. So thank you for that. Yeah, so we got the GTK Wave and GHDL installed on Chococat. That hopefully that'll help with getting simulations to run longer. There was a third thing that you wanted installed, Matthew, but I didn't find an easy way to install it. Is that something we still need to chase down? The NVC or
Well, MVC is just another simulator. It's what I've been using recently because I nuked the GHDL install on my MacBook, and it's not, for some reason it's not easy. It's fine for Intels, but I have an M1 book, so it's a challenge, and I just have to relearn that process and document better. So if I nuke it again, I'm not dead in the water. So the NVC works fine as well, but I think it's not critical. The GHDL simulator works fine, so we can use that on Chococat. So NVC is not critical.
okay, very good. I'm attempting a screen share here. Hopefully you're gonna see in a minute the visualization I made of the what the error rate does across all the repetitive tests that we're running in the current hardware environment. Um, each point represents a test of 100 uh, buckets, which turns out to be about 100 bits, I think. And so there are lots of points in each little curve. Each little curve, um, pretty much the same shape. They all start out at the bottom where the bit error rate is 0. And then uh, either right away or after just a few uh, buckets, they take off like crazy for the sky. And then of course, they hit a wall at 50% because you can't get any worse than 50% error rate, uh, not with random data anyway. You can see that there are some values here in this test that are better than others that go slower out to the weeds. There's one around the 7,000 on the scale. Not really a time scale. It's just a scale of points that I've captured that represents a particular set of gains for the loops that might be a good place to start. Uh, and some other interesting patterns here, but this does not solve the problem. It just adds a little bit of a few clues to the thinking. There's one other visualization that's perhaps worth looking at. This one here. This is the accumulators for the I side of the PI controller. You can see they stay pretty much under control up to a certain point, and then they just go crazy. So clearly, that everything above 20,000 is not going to be usable here. And the place where we think things are pretty good around 7,000 is those accumulators are still under control. So that's all consistent, but it doesn't help us make any further progress. So I think that's all there is to show about that. Um, the other thing that we talked about that we've done over last week is this solving the local builds on laptop. Uh, this turned out to be a skipped step or a misinterpreted step that actually is documented in the manual, the README, but obscure. Um, and the message coming out of the build is not very helpful unless you already know exactly what can cause that sort of problem. And what's going on here is that we didn't have the Vivado installed in the same place that the makefile expected to find it. And there's a step called out in the instructions to correct the makefile Although a better solution for that is to just actually have the tools appear where the makefile expects them to be. And rather than reinstall them someplace else, which would cause a problem with our trickery of having the shared tools on the tools volume, um, is to make a symlink. So the pull request that Michelle mentioned that I submitted yesterday is to just to clarify the documentation, to make it really clear that you have to do something about this before you build, and to suggest the Symlink solution. The Symlink was already in place on Chococat because we ran into this before and then forgot about it. That's why it worked on Chococat without any trouble and then didn't work on the local machine because we did not have the Symlink in place on the local machine. When I added it, the build worked. And I've also added that Symlink on Karapi. So that should not be a problem on either of those machines. But in the future, if we build on other machines, either people's local machines or a different VM, we'll have to remember to put that Symlink in place. I will be available for whatever kinds of uh, experiments we want to do. I don't know where to go. The math is not in my strong suit here, so uh, I'll be around to help.
Thank you. Yeah, we'll dive in and I'll do my best to keep you busy. What I can do is to try to help a little bit on the math, and I know that Matthew has intentions to contribute towards the ongoing and developing theory of operations documentation for the project. There is a start of that on the in the README file in the main repo. And we'll just keep at it over the next week and continue to document and explore and doodle and come up with experiments until we nail it. And then when we do, we'll be able to describe it, and then move on to the next steps. So it's well within our grasp. We're really close. We got the right people and the right energy level, and maybe not as much time as we would like, but enough time over the next week to make a good mark. So we'll keep at it and get it done. Let's see. Yeah, that's anything else for remote labs that you can think of?
No, just except for a lack of progress report on trying to turn up the new Pester hardware. I don't want to disrupt the other work that's going on for that, so that's still on hold for the moment.
Okay, yeah, but we know it's on deck, so we'll get to it as soon as we get a good space and enough runway to get it done. Well, thank you very much for all the amazing support and problem solving and pull requests. So very appreciated. All right, and I'd like to acknowledge our Easton is here, and the project that our Easton is in charge of is to do some documentation for things that have already gone to space. So Easton's worked on some battery characterization. So NiCad batteries in the past were successfully used on a few amateur space missions, and the performance of these batteries, it's a bunch of cells, bunch of NiCad cells, was fantastic. And there's been a lot of lore and rumor associated with these packs and these missions, dating back to the late 70s throughout the 80s, that sort of era. Um, and we decided that it would be a good a use of time and a good use of the equipment in remote labs to go ahead and duplicate the sort of the rumored procedure for measuring NiCads and picking cells that so individual cells that have similar behavior, so that the charge and discharge of these cells kind of matched. Um, because that's where you get a lot of wear and tear in a battery, is if the cells are mismatched in terms of the curves of the discharge and charge curves. So this has been a project that's been going on over the past year or so, and it's now reaching more of a stage of completion, which is good. So a number of cells were bought. Each one of them was characterized, and then Easton wrote a Python script that then sorted all of these curves into families or clusters. And this involved a fair amount of math and some learning of Python and execution. And now we have a pretty good understanding of like here's the curves, the charge and discharge curves. We've now separated out the cells into potential battery packs. They're going to now be all retested, because they've been sitting in a refrigerator for a while, just to go ahead and confirm that they're still all very similar. And then they will be exposed to some destructive testing, which will sort of like prove out the performance. And then this will be published work. So this will do two things. It will sort of celebrate and document some previous victories in the amateur citizen science space community, and also provide like, okay, so this is why these space missions had such good performing batteries, and in the future you can use this sort of approach not just for NICADs, but also maybe for other chemistries. Like if you pay attention to matching the cells in this way, and oh, by the way, here's some open source software that will help you out. Make these measurements, put it into the script. This will give you the families of batteries that you can then pick from your population. So thank you very much to Easton and the other technicians and engineers and volunteers that have been working on this. And a very special thanks to Sir Sweeney and other people that responded to our call for comments and explanations and help. So some of the original designers that are still with us were very generous with their time and support. So we're looking forward to this bit of sort of open source and citizen science work being published. And thank you to Easton for joining us today. All right. And so with that, I'd like to invite Aaron to have the floor. In any updates you want to share with us or anything that you might need, please let us know.
Yeah, so I didn't get much done this past week, so I'm kind of in the same boat I was last week. So I'm buttoning up the prototype that I demoed last week, getting that, and then hopefully start digging into the MSK and help out in that regard.
All right. Thank you so much. And if you're following along and watching, just please go back a week and find our previous video for the FPGA ORI meetup, and you can see some really neat work. This is OpenCPI. And for people that are following along, Aaron, would you like to just say a few sentences, maybe summarize about OpenCPI and the value to this sort of DSP SDR work?
Sure. So OpenCPI, it stands for Open Component Portability Infrastructure. So it's a component-based framework similar to GNU Radio, where you can use these units of work, blocks, we call them components and workers, to run specific DSP functions. And you string these up together to create an application. And we target software-defined radios. But something unique about OpenCPI is that we can take some of those workers and move them onto the FPGA to utilize the processing power of the FPGA fabric and allow you to do a lot of things at the same time and quickly. So the one of the aspects of it as well is being able to write your application with these components and then being able to deploy them on OpenCPI compatible pieces of hardware. And one of those pieces is the Pluto SDR that we've been working with. But it includes pretty much any zinc-based RF, even the RF SoC. So RF SoC, Zinc UltraScale, and Zinc-based platforms can be easily ported. So as we're developing this satellite system, we get closer to the end where we're talking about hardware. We can take the stuff that we've developed on the Pluto SDR, which is a small FPGA, and we can deploy it on a large FPGA that's kind of out of reach because of the prices of these tools that we're developing on. So that's what kind of what the framework brings, and I'm sharing it with everybody so we can get more people using it.
Yeah, thank you so much. So what's the best place on the web if someone wants to go learn about OpenCPI? Is there a good website that folks should check out?
Yeah, so our main landing page is opencpi.org. And then from there, it'll take you to various places. It's open source, so all of our source code is on gitlab.com/opencpi. We also have a forum at opencpi.dev. So yeah, opencpi.org is the main place, and then from there you can branch out to our documentation, our community as well.
Yeah, right on. Thank you so much. Yeah, I'm looking forward to I'm looking forward to the loops working so that you have
Yeah.
something that that is a little bit more sane in behavior. So we're pretty close, and I know you've been pacing us and kind of keeping at it, and also contributing your observations and help with the performance issues of the past couple of months have been deeply appreciated. So we're getting there. All right. Any other comments or questions or anything anyone wants to bring to the floor? Floor is yours.
I have a question.
Oh, sure. Go ahead.
A couple of weeks ago, you were mentioning JTAG programming of the Pluto board. And so I went out and got all the necessary bits and pieces. Had to go to Samtec for samples of .05 spacing male connectors. But I got everything, put it all together. And then when I went to get my JTAG programmers and realized they were all HPSDR Altera programmers, not Xilinx. What do you recommend? There's many choices out there for for the Pluto or for Zinc programming on the JTAG part. What do you recommend?
Well, I think that Paul is probably the best person to answer that, and he may actually still have the photographs of the actual hardware that we use on the Pluto SDR in the lab, probably still on his desktop from a couple of weeks ago in this meeting. So I'll just turn it right over to Paul to read off the recommendation, at least what works for us and what Matthew has recently gotten working as well.
Yeah, I probably do have those pictures still on my desktop. Let's see if I can find them fast enough to be of any use. Basically, they're just what comes from Analog Devices and Xilinx. And there's two gadgets you need, and they hook up together. One just provides a serial port sort of interface for the Pluto, very similar to the serial port interface that's already built into the more expensive dev boards. And the other is the actual JTAG interface.
Look for those, and because I'm sure they're really at your fingertips. And I'll let us in on our co-sponsored session next week. So at this time next week, what we're going to do is we have an event. Our meetup, our online meetup here, will be cross-listed with IEEE, and it is about the proposed rules. We're going to draft some proposed rules to renovate the 219 megahertz amateur radio band. And we've been working on this for a year or two at this point. The 219 megahertz band is a very interesting, quirky little band. If you haven't heard of it or you didn't know that we had access to it, we are secondary users of 219 for fixed digital, fairly good data rate. So the band plan from ARL dating all the way back to the mid 90s was like 50 kilohertz channels. So traditional backbone sort of things. And this band is completely unused. There has not been any significant amateur radio activity for decades, and that is because of the way that the rules are written. So the FCC rules for 219 are not great for us, and they deserve a renovation. They deserve a revision, proposal. And we were inspired by some recent events. So we saw a proposed notice of rulemaking for the 900 megahertz band from a private company a commercial entity called NextNav, and they proposed revamping the 900 megahertz band in ways that was really not great for anyone else. But we looked at that and we said, well, if the FCC is taking a proposed notice, proposed rulemaking seriously from a company like that, that we could do at least a good a job and, hope to get a good solid hearing and support from the FCC and to have this published as a proposed rulemaking so that people can weigh in. So our goal a week from today is to have a workshop and to talk through the issues, to define the problem, the spectrum management issues with 219 for amateur radio and for everybody else that's on this band, to be honest, and to propose a workable solution, and then you know petition the FCC to publish it and eventually to get rules that make this band much easier to use. So if you have time, a week from today at 10 a.m. Pacific, then we will be meeting and we will be talking about how to fix the 219 megahertz band. And then, have an open office hours about other issues as well. But that's our goal a week from today. All right, so back to you, Paul. And then I notice in chat that Aaron says he uses the Digilent HS3 programming cable.
Got that up on my screen now.
Okay, good. And then
That looks like
Paul
a
is,
reasonable solution.
yeah.
And
And then
that is the same thing.
that's right. That's yeah. So yes, this is
So that
this is
analog
what we have
devices,
in the lab today. So this is what we use for the Pluto that's in Remote Lab West.
and I have the analog devices interface already. I was just looking for the programming cable and now I have it. One other comment, just a side issue in case it turns out to be interesting to you. The Deep Space Exploration Society has been awarded another grant, a substantial grant for this is a really hard project. Ham radio does routinely with big antennas and stuff, Earth, Moon, Earth bounce. Bouncing signals off the moon of digital, analog, whatever types. Recently, we've done slow scan TV off the moon, and that works surprisingly well. Well, we are now starting a project to do the same thing off Venus, Earth, Venus, Earth bounce. One of the main concerns I have is that the protocols that we have available for digital communications are not suitable for the particular characteristics of Venus, which is very different than the moon. But we've got a long ways to go, and the project is just starting. So if anybody's interested in bouncing digital signals off Venus, we're going to give it a try.
Okay, that's great. All right. Any other comments or questions or any news to share? We're putting together our newsletter. We have a newsletter that we're going to have come out, sort of a magazine for Halloween, our favorite holiday. So we'll be summarizing all of the different work that we do. So Opulent Voice, which is the main subject of this particular weekly meeting, will be featured along with Ribbit and regulatory work and the transponder itself. So the work that's being done for the receiver in the satellite, and a summary of the work that has already been done and still does need some development, but the basics are working for the DVB-S2 downlink. So those are the four major subjects of the magazine that's being pulled together right now. So if you have any sort of updates or anything that you would like to include, like the sorts of visualizations that we saw today, I'll be making an effort to round that up and include it with some explanations, because a picture is definitely worth 1,000 words. So look for that. It'll be coming out. We have a subscription base, a subscriber base of people that subscribe to the newsletter. We have a mailing list for mainly for announcements and news announcements of meetings like this. We have a Slack that's where the daily engineering takes place, and then we have meetings like this and lots of events that coordinate with IEEE. Um, so things for AI/ML, for things like the regulatory work that I spoke about a few minutes ago, and then student and STEM support events. So that's what we're looking at for the next little bit of time is to document our work, to sort out some technical issues, and everything else. I think we're doing good. Um, lots of activity and achievements across the board. We're looking forward to receiving the plaque from the 2023 ARRL Innovation Award. That plaque will finally make its way to us. It was one of the there's two team members that were awarded, two individuals that were awarded um, on behalf of ORI, and one of them wants their plaque to be in remote labs. So we'll have some photographs of that, and we're just looking forward to Ribbit's work continuing to be useful and appreciated and recognized by the community moving forward. So thank you to everybody working so hard to get ambitious things done. It could not do it without you, and we'll continue to have this meeting and to keep reaching out and to keep fighting the good fight on open source work. Right. See you next week at the Haunted Band regulatory workshop, and then we will also have some meetings to sort of fill out some of the remaining work. There's plenty to do on Neptune, which is our physical layer OFDM link for drones, drone communications. We have an article coming out in QEX. The final version was approved and should come out, I think the November-December issue of QEX. And that's the first of two. So that's about Zadov-Chu sequences and how they're used for this particular link. And then the following article will be about space frequency block coding and explain that concept and show how it's used and the benefits. So if you're looking to learn more about OFDM or to get something working over the air, then Neptune's the project for you. Okay, thanks everybody. See you next week and on Slack.